Okay, all right. Good morning, everyone. Welcome to the session. The title is basically Physical Design Implementation Using Makeflow. And so I would be covering, what is the physical design flow and then how this Makeflow is used in the industry and how do we execute the projects and how this helps in automating the whole, implementation and all that. Okay. And myself is the host for the day, and myself Kumar, and I currently working as a senior manager and taking care of the physical design team. Okay, and I have got 20 years of experience and in the industry, and I'm currently working as well, and 15 years of mentoring experience, and I have completed almost like 50 plus tape outs throughout my career, and worked on technologies ranging from 350 nanometer to 3 nanometer with all the kind of different tools and etc. And managed a team of 60 plus engineers with 100 plus blocks and etc. And I have trained more than 1,200 people worldwide. Okay, and I have done my engineering from PhD Tech Coimbatore, and then I have done my masters from Manipal University. All right. So the agenda for the day is will be having, I have blocked this calendar for 2 hours, and but we will not be sure, like we'll be going to going all the way till 2 hours, but we will try to spend as much as time possible, and we'll have the Q&A session in the end. Okay, so the agenda is going to be, the first thing is like kind of SOC flow. What is that we do when you wanted to design a chip, and physical design flow, exactly what is in our interest for this session, and physical design project management. Let's see how the companies executes different projects and etc. And then why do we need Makefile? Okay, how it is actually going to help, and then what is the meaning of LSF? Okay, so that is something that through LSF only we launch the jobs or fire the jobs. Okay, and TCL scripting, okay, how that is actually being used in the flow. Okay, and what is the flow and why do we need flow in first of all. Okay, and then what is the flow that we follow in VLSI mentors. Okay, so this is going to be the agenda. And see, I have got a mixed set of audience here who is actually kind of all the way from third year second year students and all the way people working in industry. So please bear with me if you are kind of know certain stuff that I'm presenting, but I'm sure you will have a lot of takeaways at the end of the session. Okay, so ASIC flow. So if you look at, right, like when you wanted to design an IC or when you're working on designing an IC, okay, so the first step is to get the specifications, and once you get that specifications, you actually get into the architecture or planning phase where what are the IPs that we need, and then uh, how they are going to interact, the bus planning. Okay, what kind of the versions and all those things we would be looking at, and then once that is actually done, then we would be looking at the RTL design portion where we would actually uh, go and implement the design. So some people may reuse certain designs from the previous projects, and if the design is totally new, then we would be designing an RTL and etc. Now, when that happens, we also keep doing something called RTL verification. This is something that we call it like kind of design verification as well. And once you're done with that, then we would be moving to something called RTL synthesis. So this is the first place where your technology comes into picture. So till here, it is a kind of, you can say, common for any kind of technology. But there may be something that RTL guys might code it, which is based on the technology. But the first place that the technology, say for example, when you are choosing 5 nanometer, when you are choosing 3 nanometer, or whatever the technology that you choose, this comes over here. You actually plug in the libraries at this stage. Okay, now after RTL synthesis, okay, so what is RTL synthesis? So it's basically your RTL, basically the Verilog HTL or system Verilog is in the form of a behavioral model, and that is being converted into a gate level netlist. So under gate, or gate flops, and then memories and macros and etc. Okay, and that also we do a kind of something called gate level verification. Okay, so once you're done with that, then any chip that you've designed, that needs to be, tested. So the DFT will come into picture. So the DFT team would come and, they come up with certain testing plans. Okay, this is the architecture that we wanted to go and, insert, and then, so at the end of the, once you design the chip, once it gets fabricated, so this is how we are planning to test it. So they actually kind of, uh, insert the testing, logic. Okay, and then once that is done, the physical design team comes into picture, where they actually look at your area, what is the size of the chip, where they are going to place your bumps, audio bumps, and then IPs and all of that. Okay, and then there are certain steps that I have in next slide, which I will explain you in detail. And then we also do all the kind of sign off checks. So once everything is ready, then we go for a tape out. Okay, so this is a kind of ASIC flow that we follow in industry. Now, so let's talk about physical design flow in detail, because that is what we are here for today. Okay, so we get inputs from the synthesis team or the DFT team, because we are not the creator. So we get the design, because we are just, going to collect the inputs from someone, and then we are just going to implement the whole physical design, right? Or PNR activity. We are going to perform PNR activities. Okay, so we get inputs from different teams. So if you ask me, so we get inputs from design team on the, RTL, and then SDC, basically the netlist and SDC. And then you have to get it from the library team, which version of library that you should pick, and all that. And then you may have a CAD team, what is the kind of scripts, what version of scripts that we are supposed to use, which tool version, and all those things we'll be getting it from a different team ideally. Okay, so once you collect those inputs, so the next step is to, perform the floor plan. So floor plan is basically, say, this is going to be your design. Say now, where are you going to place your IO ports, and then, how you are going to, place the logic. You may have IPs. Okay, so say certain IP you might want to place it only in this area. So the whole thing. So planning your design. Okay, the area planning, and then the next important thing that we look at it is, what is the utilization number that we have. Okay, so all these things that we actually do in that floor plan stage. And once you're done with your floor plan, immediately within that floor plan only, we'll be doing something called PG routing. Okay, so PG routing also we will be doing it, so that like your power gets distributed. So that's the whole, intent of, the floor plan. So it's kind of area planning, placing the IO ports or IO pads, and then performing macro placements, and then doing the PG routing. Okay, these are all the internal steps. And then we have something called placement. Okay, so this is the place where we add, some pre-placed cells. It's something like kind of, there is something called indicap cells, tap cells, and then IO buffers, and then spare cells, and then we go for a automated standard cell placement. So you may have a, design with kind of 1 million cells. Okay, so you cannot do manual placement. So whatever that we have done in the floor plan stage, that is only for a bigger cells, like kind of macros, IPs, and etc. But when you have a standard cells, it may be big in count. So we let the tool perform the placement. Okay. Now, during that whole process only, so we look at, there are a couple of things here. One is kind of, say, you can say timing. So the first thing the tool looks at is timing aspects of it, and then your congestion. Okay, and then you also look at your utilization. Okay, and then you also look at your power. Okay, what kind of, what is the power consumption, is it like on the higher side, or you wanted to target the power. And then you will also look at your VT percentage and lot of things. Okay, so because why VT percentage, this people neglect it. But remember, LVT or ULVT or ELVT, so these are all the cells that will actually be, they will have a lot of leakage. So you should actually know. So LVT would be maximum 5% is allowed, and ULVT is going to be 0.5%, and ELVT is going to be just in terms of count, maybe 10 cells or 100 cells depending on the requirement. So this is a kind of thing that we look at the end of a design. So that means you should not enable any of this, and if your design is already having these VTs, you should actually look out and watch out what is the growth that you see. So placement is basically targeting the timing, congestion, utilization, and then power, and then VT percentage, and then there are many more aspects. Okay. And once you're done with your timing, the placement, okay, then the next step is something that we call it like kind of the clock tree synthesis. So you have a data path in a design. Say for example, you have a design like this. Say this is your design. Say this is your rich to rich path. Say you have a design something like this. So now this is data path. Okay. And this particular thing, so this is something that we call it like kind of say clock path. Okay. Now, when I say clock path, so at the time of placement, we focus only on the data path optimization. We don't bother about your clock tree because we treat them as a ideal. Okay, assuming all the clocks reaches the flop at the same time. Okay, now during the clock tree, we go and build the complete clock tree during the CTS stage. Okay. Now, when I say that, there are certain targets. See, like how we have a placement. So you have all these. Okay. And when it comes to CTS, you have to give a certain specifications, like kind of, see, you have got insertion delay. Okay. And then your skew and what kind of cells that you are going to use for clock tree building, and then what kind of routing layers. Okay. And then you have which and routing rules. So default routing rule is basically single width and single spacing. When it comes to NDR, we say double width and double space, double width and triple space, or you might even build a clock tree with shielding. So all the things that you need to provide as a spec. So the goals at the placement stage is different, and then the goals at CTS stage is different. So sometimes you kind of get questions like, why do I need to do CTS? Why can't I do it along with the placement? No, that is not possible, because the goals of this each stage, placement and CTS, are totally a different one. Okay. So this is only with respect to your clock tree. Now, once you build your clock tree, you get your skew propagated. So we just said like clock tree is ideal all the way till CTS, right? Anything that you follow from synthesis to GDS, it's synthesis to CTS, the clock tree is said to be ideal. Now, the moment you build your clock tree, your clock is propagated and the actual skew is calculated, okay, by the tool, based on the number of cells, what layer is used for your routing, and what kind of NDR. So it's everything. Okay. And then we actually perform routing. Okay. So where we actually go and connect the nets basically using the metal wire. So you have a kind of metal 1, metal 2, metal 3, and different metals and all that. So we would be using that as a wires, and then connect, establishing a physical connectivity. Okay. So physical wiring or connectivity, that's the main thing. And then once you are done with this, okay, so now what is the goal? Okay, you might question me, Kumar, it's like kind of so we talked about timing, congestion, and all that, placement, but do we really bother about them at CTS as well? Yes, the answer is yes. So each and every stage, you have to look at your timing, and you have to look at your congestion, and you have to look at your utilization. What is your utilization, and what's your VT percentage, and then power, and all that, if you are working on a critical designs. Okay. Now, when it comes to routing, the goal of the routing is bringing it, targeting zero opens and shorts. Okay. Zero opens and shorts, and then zero DRCs. Okay. and and along with that, you should again look at your timing, but remember, you don't look at your congestion number at the routing, because congestion is nothing but your early estimation of your routability. Okay. So the moment you are in the routing stage, we would always look at only the opens and shorts and the DRC. So some people I have seen, kind of, they're looking at congestion, even after routing, they come and say, Kumar, I have a congestion of 2%. And that, what the only thing that I ask is, what is your opens and shorts count and the DRCs count? That's a basic thing. Okay. So each and every stages have different targets, and then the QA checks that you need to do. Okay, and again you look at your timing, and again, as I said, like kind of the opens and shorts and DRCs and all other things. Now, so you're done with your routing. The next thing is basically a sign off checks. So you have a different sign off checks. So if you ask me, so you have got your physical verification checks like DRC, LVS, antenna, okay, and there are many such checks. Okay, so people may have a soft checks, ERC, and etc. And then you have on the LEC front, okay, you have a synth to route, a gate to gates LEC that you need to run. And then when it comes to STA, so you have a kind of both setup hold, DRVs, and then crosstalk and everything that you look at it. Okay, so you need to ensure that you run all the sign off checks, and then you go for tape out only when it is clean. Okay, and so people might just feel that it may be a simple thing, but remember, you may be see, like, look at the design from a full chip angle. Say for example, if this is your design, okay, you may have a different blocks inside. Okay, so you may have a different blocks. Okay, say kind of say this is block A. Okay, so this is block B, block C, say block D, block E, F, G, H, I. Okay. Now, each one of you will be assigned, say, assume one block. Okay. Now, when I give you block, that means you would be owning this whole implementation, and then you would be, kind of designing and implementing the whole thing. But now at full chip level, once your block is clean, once your block is clean, then you have to give the design, the collaterals back to full chip. Now they run your STA from a full chip angle, and then they run PV from a full chip angle. Even if your block is clean, you may have a violation at the interfaces. See, you may have a ports, or the shapes coming close to the boundary. So all these interface things also needs to be cleaned. Okay, so you have to be make sure, once your block is clean, we will not be able, we will not be taping out, because your full chip needs to be clean. So that means, say all the blocks are clean, but this E is not clean. So that means we are yet to go, we are the design is not a clean. So as a full chip only, we go and do tape out. So you need to spend, this design has to, close, and then we go for a tape out. That is a common procedure or common process that we follow in industry. Okay, so in the interest of time, let's move on. Okay, all right. Say now, assume you are working for a big giant company. Okay, giant company. Say for example, like kind of I don't want to take any company. Say assume the company name is ABC, and they have got speedy team strength of say 50 people. Okay, but they are executing multiple projects. Okay, so when I say multiple projects, okay, what is this meaning is, there may be a team which may be working on a project A, which may be targeted on 7 nanometer. Okay, and it would be planned to tape out in March 24th. Say March 2024. So it is going to have tape out in say next month. Now at this moment, say they might be a team working on this project in a full swing, because this is the project that is basically going out first. Okay, now there may be another project again there. Okay, so which may be planned for tape out in the month of June. Okay, so now if you guys look at companies like Qualcomm, and MediaTek and also, they work on multiple chips. Okay, so they actually have a kind of this kind of mechanism where one chip might be going out and another chip might be going out in next 3 4 months and etc. So now assume this is a 5 nanometer project, and this planned in June. Tape out is planned in the month of June 2024. And now at this point of time, they might be estimating that they might need 20-member team, but they may not be having all the 20-member working at this moment here. Okay, I'll come to you. I'll come to that point later. Now there is a next project that is actually kind of in the initial phase, or probably in the very early phase, you can say. Now that is being targeted in say N3. It's basically a 3 nanometer, and now that is being targeted in the month of August 2024. Now they at this moment they might be looking at say 10-member team. Okay, Now, what is meaning is all these projects would be executed and needs to be taped out on schedule. Okay. Now, how are they going to, plan the whole team, and then so that like your project, the first priority is this, and the second priority is this, and third priority is this. Now, so this project gets taped out. That would be the first priority for the company and the team. Now, what they do is whoever is available, okay, now or whoever they have planned for this project activity, they would be actually asked to work and design, close the designs, and then make sure all they support other designs also, so that the whole project gets taped out on time. Now, when I say that there may be 25-member team might be working on at this moment, and I might be taking, there may be 10 more people for last minute DRC cleaning, okay, or I might be taking some timing team, okay, for preparing ECOs. So maybe 5-member team for next 2 months, and then I may have IREM team. I might have a 2 to 3 people. So, and then regular PD team. So that is how the team composition going to be. Okay, so when you say 25, they might be started with PD team, but now they might be busy with implementation and then other issues and etc. Now, if they in case if they have a lot of DRCs and then PV related issues, then we need people who would actually kind of take that and then help this team. Okay, so these are all kind of the extra resources. This is the place where the services companies will come into picture. So people say, okay, I have a requirement, say kind of say for example now say Intel. Okay, now Intel is actually executing this project, so they have a 20-member team, but they feel that okay, they need little more helping hands to make this on time. What they do is they just go and ask services companies that hey, I need 10 PD resources for 2 months. Okay, and they tell that I need say kind of certain with someone with certain skills, say for example 5+ experience and knowledge of 7 nanometer DRCs and who worked on it and things like that. Now again, they also say that like kind of I need 5 STA members, and things like that. So this is how your services model works. So when there is a project that is getting executed, there may be issues which might need extra helping hands, and immediately they cannot hire. So I have to tape out on in the month of March. Now if I try to hire, the person may not be joining immediately. Even if he joins, he may not be helping, because he needs to ramp up on the flow and a lot of things. So they might be kind of, so the project won't tape out on time even if they go for new hirings. What they do is they just approach the services companies like kind of Capgemini, Wipro, and then you have HCL, and then there are many services out there. So they actually come on board and then they actually try to help. Now you might ask, okay, Kumar, this project is now say we are actually done and we are kind of taped out. Now what is the next thing? So the next thing is kind of this project would be start getting started in full swing. But you might ask, Kumar, so when this project is being executed, will people work on this project as well, or nobody will work on it? Now the answer here is people would be working. There might be some planning activity, okay, so maybe area planning. Okay, there may be a lot of discussion with IP vendors. Okay, say this is my area. Okay, now this is the width that I'm actually having, this is the height that I'm having. Now my IP sizes are this. So now what is the area that is available for all the other blocks? So the top level activities would be happening. That is one aspect. Okay, and then there may be a team who would be working on the flow flushing, because this is a different technology. So this project is done in 7 nanometer, and this project is executed in 5 nanometer. Now you know what, the scripts are going to be different, because the 5 nanometer requirements are going to be completely different than 7 nanometer, and then the library is going to be different and all that. So you need a team who do flow flush. Okay, so they just take your design through the flow. Okay, and then ensure the flow runs smooth. So remember this, actually when you go from one technology to another technology, the tools have different settings. So you have to internally set certain things, and then some versions, say you might be working on, say, kind of, say ICC 223, say kind of service pack 1 or something like this, or here if it is a innoverse, so 23 dot 1.1, something like this. So the tool versions, okay, may be different for 5 nanometer, okay, when you wanted to target. So you might have to pick a different tool version. So overall, you should have a team. So as of today also, so it is a kind of, though there are team which is kind of working full swing in this project, there may be a team which is a small member team, say maybe 5 to 10 members team, who would be working on this project as well, looking at your area planning, and then flow flush, and then looking at your IPs, whether is there any issues, constraints, and then they interact with the customer who buys this chip. Okay, now this is how it is actually being planned in the industry. Now once this project is done, the project A is done, then they move to complete team would now take a short break, and then they move to the new project, and then it gets started in full swing. Now again, in the month of April or May, they look at, okay, how critical blocks are, will they be able to complete it in on time or not, and by the time they let the service guys go back to their parent company. Okay, so they will finish the project and they go back. Otherwise, if they are actually kind of, they realize that, okay, there is a critical phase, this team needs support, they have to support this project also, then they might continue. Okay, now again the work completely gets into full swing, and then we try to look at various things, whether how the blocks are closing, where are the problems, who is going to fix that problem or solve the problem, or do we need any help from different teams, like kind of RTL teams, do you need RTL teams support here, or do you need a synthesis team have to redo the whole thing, or constraints, and many other things, ideally speaking. Okay, so this is how the whole projects that are being executed in the industry. Now coming to this, the project C, it is kind of at this moment, again there may be a 5 to 10 member team who would be looking at, okay, what are all the new technology challenges, okay, what is your integration guidelines, and then what should be your block size, okay, and then what is the libraries that you are going to use. Now if you guys look at, so in 7 nanometer we have only two flavors of libraries, one is 6T library and another one is 7.5T library, whereas here in 5 nanometer I have worked with only 5T libraries, and here again in N3 there are different heights of library. So if your design is timing critical, so which library that always pick the higher track library, the high. And then if your design is normal, it's not so critical, but so you wanted to optimize your area and power, so you might use 6 track library. So all these kind of decisions that would be or experiments that we would be doing, and your managers would take a call, okay, whether they should go with 60 library or 7.5T library, and etc. Okay, so when I say all these, right, like, you might be looking at, okay, so physical design is just only a 50%, but the concepts and the knowledge that you have, issues debugging and all that, but making decisions, or planning the projects, okay, and then there may be a team member who might be falling sick. Now who's going to back up them? So there are, planning is actually the next 50%. And then your libraries, see, you may have something, you might have heard something called a PDK, where you have, where you have inputs which are continuously changing. Okay, you may have a tick files and DRC rule decks, all that are might be continuously changing. So you need to deal them, okay, so you might have already closed your block, now there may be a DRC rule update. So you run that, and then you see hundreds of violations. That again, you need to make a call. Okay, how am I going to do that? Now, when you fix the DRC, will you get into timing issues, or you want to do something called ECO route, and all that information that you need to look into? Okay, now coming to this N3, so you need to interact with Foundry. So as I said, like this 5 to 10 member team, they have to interact with Foundry. They have to ask for a PDK. Okay, and then once they get it, you need to interact with your tool vendors, maybe Cadence, Synopsys, which tool that they have to use. Is there any baseline flow that the tool vendors can give to get started? And then people will take like kind of the design is that RTLs are ready for your 3 nanometer projects. And then what about your DFT team, what kind of are they ready, what and all the timelines that they are actually working on. Okay, and all these things would be kind of a big thing. Now and then your integration guidelines, say your blocks, say there is a block width. So there are certain guidelines that when you're designing a block width, or when you're coming up with a block width, and when you're coming up with a height. So up to 16 nanometer, okay, we never had any kind of restrictions where you can just choose the height and width as per your requirement. But 7 nanometer onwards, we have the block width has to be certain measures, certain values. And then block height also should be certain values. And then you may have IPs, say for example macros and everything, so you cannot place them randomly the way you used to do. You have to actually place them in a certain locations, because otherwise you would have the base DRC issue. So there is something called, when you say DRCs, we have a base DRCs, okay, and then you have metal DRCs. Okay, and then when you say this, so there are different layers in the implementation. So you have base layers like NVEL, P plus, N plus, poly, OD, and contact. And then do you have any kind of issues that you have with the base layers? Because base layer DRCs needs the whole rebuilding the system block. Metal DRCs, it's something that with respect to your routing, so you can actually incrementally adjust. So people have to meet the base DRCs at the floor plan stage itself. So they have to follow the block integration guidelines, and then macro placement guidelines. And then there may be a checks, okay, which can be catching the issues upfront. Okay, all these things. So you need to get all these information. It's not like, okay, just we are getting a design and we are just executing. That is not the thing. So at engineer level it might be okay, but when you grow as a senior engineer and when you grow as a lead, you have to start looking at, okay, what are all the items that I need to look at upfront, so that like my execution can be smooth and seamless. Okay. Okay, I think I would like to stop here for question and answers, because we just covered a lot of content. Any questions?
Hello, sir. How to integrate this different blocks?
So we actually do something called partitions, and then we push it. Then so it's kind of the, say for example, if this is your design, okay. So there would be a full chip person who would be doing this whole partition and all that informations, and then they would actually, now say all these blocks. Say the first step is full chip planning. Okay, full chip planning. Okay, now the partition, so they just give them the area and then the IO ports location and all that. Now the block owner takes that area and he builds, so block level P and PD. Okay, now he actually goes and completes all his the block, implements the design. Now he actually shares the left and GDS, and then your ETMs. That is nothing but your timing model for your blocks. Now, full chip guy actually starts the integration with all these data of all the blocks. So he builds the full chip again. So what they do is, first they come up with the area. Now they divide the area into smaller ones for blocks. They give it to a block owners. Now block owner takes a month or two, closes the design. Then he actually takes these data, left GDS and ETMs. Now he integrates, okay, and then he actually performs the sign off checks. Okay, so, and again in this partition itself you have different ways. Okay, one is abutted partitions, and then channel based partitions. So it depends on what kind of chip that you are actually working on.
Okay, thank you.
Okay, I see a lot of questions in the chat box. Okay, so which are input we'll get it from DFT, sir. Okay, so from the DFT team we actually get a lot of input. Say one is like kind of scan def. So basically scan inserted netlist. Okay, scan inserted netlist is the first input that you might get it, and then you get scan def. Okay, and then you have to so because there is something called scan chain reordering that we do in the placement stage. So without scanf we won't be able to do it. So from the DFT team we do get this. And then test mode constraint, test SDCs. Say for example you may have a scan shift, okay, and then scan capture, scan at speed. Okay, so these are all the different test SDCs that you get it from DFT team. Okay, so that is answer for that question. And then we have how to check the VT percentage in ICC2. So there is a report threshold voltage group. So report, there is a command called report threshold voltage group. That is a command that you can use to see your what is a percentage of things. Okay, and so the next question is what should be the timing number after route stage. It should be clean, ideally speaking. The timing numbers, it should be ideally clean. So there is, otherwise it should be, I always look at, say the WNS should be always less than your uncertainty value. Okay, so that's the kind of thing that we look at. But again, it depends what kind of path, what kind of cells that are used in that path, how big is the, how long is the path, and how is the placement of that path, how the routing happened. So there are many other things before we say anything. But the preferred, I actually treat it like kind of WNS should be less than uncertainty to move forward, or you can say off of your uncertainty. So it purely depends on the designs. Okay, and so, how to check how many pre-placed are used in the design? I'm not. The question is not clear, Darshan. Okay, and
Hello, sir.
then yeah,
Sir, if the in the block level, if you are meeting all the requirements, and if you are getting issue in the full chip level, how exactly we can redo? Like,
you don't
what
need
will
to
be
read.
done?
No, that is actually, it is like kind of, that's why we do phase by phase. So it is like kind of, if you look at the question here is, say you have a, you're very close to tape out. Now your full chip level issues, the block level is clean, but the full chip is seeing some issues at the interface. Now how do you do it? You know what? When we say physical design implementation, we have, say this is your tape out date. Now till here, say we have a 2 months before. So this is going to be a final phase. Okay, and then say this is going to be a pre-final. Okay, and this is maybe a kind of trial phase. So if you look at, right, the final phase, you should have identified all the issues in the pre-final stages only. So last 2 months, whatever that you should have known your block. Okay, these are all my block issues that I have to take care. From a timing perspective, you might have a path groups, you might have a congestion. Okay, this particular module is going to create congestion, so I need to take care and all that. So by pre-final, you should have got a recipe that closes your design. Okay, so to answer your question, the interface issues also should be identified during the pre-final, so that your final runs can take care of all that. So that is the ideal way of you executing your implementation. But sometimes it may not happen like that. If you see something, you might have to incrementally work, or some blocks we might have to restart due to some bugs. So you might have to take care of all such things. The answer is, ideally you should have identified all such issues in the pre-final stage itself, so that your final runs can be smoother. But now in case if that is not caught in pre-final, now you are seeing something new in the final stage, then you have to work with your full chip PD engineer, or your lead. They will guide you better. That's the way, how we can make sure we redo and still meet the tape out date deadlines. Okay, I believe I answered the question. And then next question is, what is meant by 6077.5T levels? That is basically standard cell library heights. Okay, so that is basically a standard cell library height. So you will have standard cells with the different heights. Okay, so this may be 60, this may be 70, and this may be 7.5T. And this, people call it like kind of say high performance libraries. So the higher track is called always high performance library, where you will have a lesser delay, bigger area. And where this is kind of, we say high density library, where you have a little more delay, and but you get benefits of area and power. Okay, and then why are macro
Excuse
placement
me,
better?
sir.
Yeah, go ahead.
So regarding the pre-placed cells, I mean, how to get the count of the cells used in the design? I mean,
Maybe that
count
no
of
no
pre-placed cells.
no, I think that let's take that question last. No,
Okay, fine,
that
sir.
is getting too much into that because I have a lot of audience, okay, who might be
Okay, fine.
looking for certain things in this make flow. So that you are asking two pure PD questions that we will look into it. Okay.
Okay,
Okay. And then why macro placement guidelines are changed in lower nodes? I think these are all something related to PD, complete PD. I will take these questions in the end. Okay. How many days for physical design? Okay. So so there are questions which, okay, I think there are a lot more questions. I'll do this actually. So let's take this questions uh, that are too much technical towards the end. Okay. Please keep sending the questions. I'll try to answer in the end. Okay. Now, so the next important thing that we are all here is like kind of what is make file based flow? Why do you need it? Okay. Okay. So before that, now let me give you a scenario, a simple scenario. It's like kind of see you are actually a PD owner. You're actually owning a block, so you're a PD owner now. See, you have got your block. See, you have done your, you have got your inputs in the morning, and then, say morning you have started, you got all the inputs. Now you are doing a floor plan. By evening you have completed all your floor plan and everything is ready. Now you have just fired the run before leaving your office. Say, assume you are leaving office at 6 p.m. Okay, and you have just fired the run, say floor plan, because floor plan, it's not just only arranging macros. There will be power routing, and takes a lot, good amount of time, and then there may be internal checks and all the things. So assume your floor plan run time is say 5 hours. Okay. Now say you fired the run at 6 p.m. and you kind of reaching back home, you're on the way home and things like that. Now say after 5 hours, say for example around 11 o'clock after your dinner, you're just logging in and checking the runs and it is okay. Now you are actually going to fire the next step. So it's called pre-place. Okay. Now this pre-place is basically adding the end cap cells, tap cells, and then doing a couple of other important steps. Now say this is runs for next 2 hours or say 3 hours. Now this would be completed at say kind of 2 o'clock or say or 3 a.m. Now you have to fire the next run, which is next stage, which is kind of placement. Now likely that you may not be awake at this time. We may be awake when it is in the final phase, but if you are in the early phase, then you may not be awake. So now what you need to do is, say, assume you are getting up at say morning 7 p.m. Sorry, 7 a.m. Okay. Now your run got over at say kind of 2 a.m. Now 7 a.m. Now there is a gap of 5 hours. So if you would have fired run this place, you would have the run would have got off way through. So we actually look at, assume your placement takes 12 hours. Runtime normal time is 12 hours. So now what if you would have fired this run by uh, immediately after this thing, you would have got the placement completed by 2 p.m. or say 3 p.m. after your lunch or something. So you can actually have a time to analyze the results and etc. But what happened is you did not have, you're just firing the runs one by one. So you got up and then by the time you log in it is a 9 a.m. and you fire a run, it comes at night, midnight, 10 o'clock again. So you need a flow where one stage after, once the stages gets over, you can automatically, the other stage has to get started, and then the same thing continues, and it checks there are certain prerequisites whether all the files that are needed for your place is present and things like that. So and once it is done, it also checks a QA whether all the data that is needed it's kind of dumped or not. So basically you need to have a flow where you kind of run one stage and it looks at each and every prerequisites, completes the stage, and then performs QA and then move to the next stage. Okay. So flow actually helps to make sure you continue the runs without wasting your time. Okay. So now instead of you running one by one, you should have something. Say for example, if I say make route, or say I just want to fire the route immediately, but you know what? it would actually run each and every stage. Say for example, you have a floor plan, placement, CTS, and then route. So I just want to execute the last command where all these stages should get automatically executed. First, it should run FP and then place and etc. So the make based flow helps in going back and checking whether the stage is completed or not. Okay, now if it is completed, okay, fine, it goes and runs the next one. Now if this is not completed, then it is actually reruns the whole thing, the FP, and then continues. So it actually, the make file based utilities basically helps in defining your flows and what needs to be executed first and etc, and it actually runs one by one. So you definitely need the flow to do efficient execution and well managing the timelines. Okay, now if I don't have a flow, you know what, I may not be able to tape out on time. That's a basic thing. Okay, I need flow so that like I can actually go and plan my schedules or the deliveries or the tape out dates on time. Okay, now this is going to be the way we execute projects. So now make file is going to actually help me achieving that. So make is basically a Unix utility, or say it is a kind of, you can say, another program as a kind of another language that is designed to start the executions which is defined in the make file. Now it is a kind of special file which contains the below information. So make file will have the targets. Okay, what is going to be the first target and what is the prerequisites for that, and the next is what are the each target prerequisites, and once that is all met, what is that you wanted that to execute. Okay, what is it you wanted that to execute. Okay, now the file, you should have the file called make file in your run area. Okay, so that that file should have all the, what do you call, targets defined and the flow in the order wise what it has to run and all that. Okay, and I'll show you guys what is there with me actually. And it re-executes the particular target if the input timestamp is changed. Say for example, your floor plan was run a day back, so it might see that the right timestamp, and then it might redo it because there may be inputs that might have got changed. Okay, and as I said, it executes each step in the defined order. Okay, so which means you don't need to sit in front of laptop and executing one by one. That's the main thing. And you can actually say for example now, um, okay, I'll come to that. I wanted to give some practical side of it. So this is how this is how we are using the make file based flow. And let me just show you guys what we have. Okay, now if you guys look at this particular thing, I have defined a kind of, I have a different stages. Okay, so if you look at, so we have something like kind of, readme that will have, say these are all the stages. Say for example, to import your design, say make import, that is supposed to be run first. And then if you want to perform macro placement and then writing into a def, then you should run this and then write out the def. And then to run the whole make floor plan, you just have to say make floor plan, and then to run pre-place. So these are all the stages that actually I have. Okay, I have defined it. So me being a flow person and then designer, so I know and I have got a good experience in defining all such things. So I actually kind of define these stages are the apt for me to execute, or say my team to follow. So assume I'm kind of the lead or manager. Now I have a team of 20 people. Now I may not be able to ask everyone to execute their own way. That will actually make me fall behind in terms of schedule. So I have this flow which is kind of, the cat team have wrote it. Now we I my you know the way the communication goes is, hey team, I want you guys to follow this flow and execute your whole design. Now, if you have a problem with your design or the flow, get back to the flow team and they will help you out. That's a basic, communication that we share it with people. So, in the interest of time, I'm just going to limit this here. So, make import is going to be my first thing, and make pre-place, and then make floor plan, pre-macro place, and then make pre-place, and then make place. All these things are basically the stages that we actually have it here. And now if I have to show you the make file that I have it, so it's kind of import. That's the first stage, so where I don't need to worry about it. Now the next thing is here, I have got import. Okay, so to run pre-macro place, I should have completed the import. Now that is how I am defining my prerequisite. So if I wanted to run floor plan, I need the import to be done. Now let's see my next targets. So pre-place. Now this is going to be my requirement. So if I have to run, my floor plan should have been completed. That is how I am defining the dependencies. That is a basically order that I'm actually showing here. I mean, defining in that make flow. Now this would actually go and actually, say, create the whole, design and, whatever that you wanted. And now it actually invokes the tool automatically and source it. And then it automatically dumps the log file for us. See, in industry, you have something called logs. So you will have, say, for example, now I have got this floor plan.log. So when the runs are in progress, you will have to go back and check here. So this is how these are all the log files. Now it will actually have all these things. Actually, what is the tool is actually doing. So the flow is basically going to perform each and everything one by one and etc. Okay. Now the make flow is what, which contains all the kind of stages which I showed you just now, all these stages, and including my extraction and including my STA runs. And you can actually configure the number of corners and everything. And then you have got your DMSA flows also kind of completely brought it in. And then I do have got the ECO rolling in. Okay. So the way you look at these are all the stages that you can actually, so you can come up with your own stages. Okay. So if you are working on a project, yes, definitely you can actually, learn, define your own way of it. But let me tell you this, the whole defining the flow and coming at the flow, it takes a minimum a year plus, because you need to plan, okay, what are the inputs to the floor plan, that all the, you need to check it before running it, and then the scripts has to follow, and then, variables that you need to define, how are you going to use all that. So the whole thing, so coming up with the flow, so you working on the flow is not an easy thing. You need good amount of time to architect the flow, and then, what order, what steps that you wanted to execute and all that. Okay. Okay, so this is exactly what I was just talking about. So at VLSI mentors, how I have written the flow is, so it is like kind of this, all these are all kind of, the PD flow, PD targets. Okay, so these are all my PD targets. Okay, which is kind of, I have to follow. So if I just say make route top, so I have just created my design area and everything, all my inputs which is needed for your input is there. Now if I just say like kind of make route top, what it will do is it will just go and run import stage first, and then the next is going to be a make floor plan, because this is a kind of optional stage. So this is kind of optional, so remember this. You can actually define which are the must thing and which are kind of optional stages also. So this is only if you have a macros and you have to do a macro placement. Otherwise you don't need this stage at all. Okay. Now assuming that you get the push down from your design team, the top level PD team. Okay, so make floor plan, so it runs import first, importing your libraries and then your designs, and then your floor plan and all those things, and then it performs your floor plan activities like kind of the area IO ports placement and all that, and then PG routing and etc. And then make pre-place would do your placing those pre say the physical cells. Say for example, you have got end cap cells, tap cells, IO buffers, and then spare cells, and then you may have your low power cells also would be getting placed it over here. Okay, and then you perform your standard cell placement with the help of tool, and then your clock tree. So it all executed one by one. Okay, it is not that you have to sit and source invoke the tool and run it one by one. You might miss a lot of warning, errors or warnings that might be reported by the tool if you're running interactively and if you don't see the log file. So we have got, these are all the targets, okay, with respect to PD, and these targets are with respect to your STA. Okay, now if you look at here, say we have got extract folder, so you need to perform your RC extraction. So that is going to be your spiff format. And remember, yes, when you say spiff, you have got multiple spiffs. So you have got parasitic corners like kind of C worst, C best, or C worst, or C best, and again typical. So you might be having a different requirements, or see your timing sign of criteria, I can say. Now you need to extract the spiffs with respect to that. You may have to extract it again based on say 125C temperature or the N40C, or different temperatures also you might follow at the time of extracting the spiff. And then you run your STA. See, you may have different corners. See, you may have a 10 setup corners, and 8 hold corners, something like this. So now you need to run all such things. You cannot run one by one manually. So there may be a targets which is kind of something like this, where you will have your runs that is kind of executed automatically. Okay, and then once you are done with this, so this is your just pure STA. And then you might wanted to follow the timing closure flow. So I'm sure some of you are actually working in industry, and majority of the people are kind of looking to get into industry from the registration that we have got. Okay, so the DMSA actually helps in coming up with your timing close, timing ECOs. So it is basically you have a physical aware timing ECO generation. So it helps in closing your design after your route. Okay, so you can actually run DMSA after you're running this, and then it writes out your timing ECOs, okay, for your design to close, for you to close the design. Now these timing ECOs will have to be rolled in ICC2 again, or say Innovus, whatever the PD tool is. So now that is something we call it like a ECO implementation. So we have got make role ECO, which means it is automatically going to implement your ECO. So I can say these three, you can say like kind of sign off STA targets, and this is kind of ECO implementation targets. And then I do have kind of the targets which are kind of say make DRC to run your DRC runs. Okay, and then you do have your LVS targets, where you just go and run your LVS. It performs ICV based LVS checks. Okay, so we have got complete synopsis tool sets. Okay, and we use IC validator here for our learning purpose, but in industry you may have a caliber that is being used as a sign off tool. Okay, but remember, these flows are basically designed in a such a way that you can plug in any tool. That is a beauty of it. You know what, in industry, I'm talking about now industry. So in industry, see, you may have see a design, your full chip like this. You may have a critical blocks. Now assuming this blocks are using say ICC2, okay, for building the block. Now say this particular block is using Innovus, because they, one of them may be critical, or these are all the other things may be critical. There are certain things that they decided to use a different tool for different blocks. Now the flow should be helping the designers in a such a way that they can actually choose say the tool underscore name, say ICC2, or say Innovus. So you should have an option to choose the tools. Then the flows will automatically pick the respective scripts, and they will execute. So now the flows has to be kind of flexible. When you are writing a flow, the flow should be flexible in deciding the tool that you wanted to use for your implementation. Say some simple, right? Say for today, I have ICV with me. Now I'm actually using this ICV, but tomorrow let's say I have a caliber. Now I just have to make very minimal change that I should be able to use the same thing. In fact, the designers won't even know what tools that are being used sometimes. That is how the project execution happens. They look at, okay, I'm running this, okay, look at the log file, reports, and etc. So um, that is how the flow, when in case if you're interested in writing the flow, you should actually look at how flexible you can actually make it, and you can actually keep multiple variables and change things like that. Okay, so these are all the physical verification targets. I'm just listed only few that is are important, but we do have ERCs and then many other checks. Okay, and then let's say you wanted to redo all the runs. Say for example, you have got done something, but now you want to redo all the runs. You know what you need to do? Just say make clean, and you can actually redo all the runs from the starting. Okay, so that is how it actually works. Okay. Okay, I would like to take the questions in the end, please. Okay, because I wanted to show you guys the practical also how I run it, and then you guys can see it, so that like I'll have it last segment dedicated for Q and A's. Okay, so the next thing, LSF job scheduler. Okay, um, so what is this LSF? So I'm sure many of you are actually looking to get into industry, but if you ask me, you might have learned what is VNC, or you might know the Linux environment. You might be firing the jobs in the same machine and things like that. But when it comes to industry, you know what? There would be a dedicated servers. Okay, there would be a dedicated servers which will be running the jobs for you. So now, simple, right? Like I have a 50-member PD team, 50 PD engineers. Okay, now all these persons will be firing the runs, right? Now who's how you are going to control? Now some persons, okay, may be firing the heavy runs today, but they might be doing the complete analysis tomorrow. Okay, but how you would be, you being IT manager, okay, so how will you allocate your servers? Okay, now the way the infrastructure in industry is, see, you have got a servers, actually servers, all these servers which are available for any of your PD engineers. All the 50 engineers can fire jobs in any of this. Okay, so simple, right? Server 1 can run 30 jobs. Okay, so you have got a 30 different engineers, or 30 different runs that you are firing. So server 1 will be able to run 30 different jobs. Anything beyond that, it will be slow, or it might not be able to support. Now server 2 can run another 40 jobs. Okay, now what? So you need to have a mechanism where all the servers that are loaded equally. It should not be like, okay, there are 30 jobs running in this and 40 jobs running in this, but these two are ideal. It is just sitting ideal. Okay, so what we do in industry is, there is something called LSF utility, where we that is actually called load sharing utility or facility, which is kind of decides, it has, okay, these are all the servers that are available for me to launch the job. So when you fire a placement run, it actually goes into the server. Okay, now say another person fires a routing run. Okay, now that might get into server 2 now, because the LSF, so it's kind of it's all the 50 engineers will have a VNC session individually, so they actually fire the job. Now it goes to the LSF as a request, and then LSF actually dedicates, or decides on which server it has to go. Now say for example it is completely full. That means what? This LSF will close the server for new jobs. So new jobs are not allowed because it is already full. It will try to see other servers and then launch the jobs in that server. So LSF is one of the important thing that you should be knowing. I'm sure if you are getting trained in any place, or if you are in a college, or you are not in from VLSI background, then definitely you would need to learn about something called LSF, where you actually, when you're firing the jobs, it has to go to LSF, and LSF will decide on which machine it has to run. Okay, so it's LSF distributes the work across the existing IT resources. When I say IT resources, it is a server farm. People call it like a server farm. Now, these servers, would be run in a data centers. There will be a particular data center where you will have all these servers would be running over there. Okay, I'll just show you how a server environment would look like. Okay, so your server environment would look like this. Say it is a kind of racks in which you will have the servers which are kind of placed with completely AC controlled. Okay, and okay, you see this. This is going to be your server. Okay, now with this LAN cable and how you are regularly operating the things, right? Say this is one server. Okay, now if you look at, this is kind of one server, this is second server, now this is third server, so now this is server number 4, server number 5, server number 6. So the whole data center would be having a servers which are kind of placed like this. Say simple, right? You have your Amazon cloud, or Google cloud. That is one. Now for example, Facebook servers. Facebook is very big website, right? Like how, that needs a bigger data center. So they place all these servers now. So the same way, even when you are firing the jobs, they would be actually kind of supposed to go into different servers depending on the load. Okay, so LSF would actually helps in distributing the work across the existing resources. Now, more reliable workload performance. Say for example, it can balance all the servers, so your runs will come out. Okay, and it balances the load and allocates resources efficiently. And then LSF cluster manages resources, okay, accepts and schedules workload and monitors all the events. So remember, I'm not sure if you guys ever got a chance to learn something called multi CPU. Say when you're running a job, say you can actually, it's called multi-threading. Okay, so we might run the jobs with say 8 CPUs, or say 16 CPUs, or even we run it with 24 or 32 CPUs also. Okay. Now a simple thing, for example, if you are having a, say, the Redoc for IREM, that we use this Redoc tool. Now, say some of the companies have very big designs. They actually need 500 CPUs for your IREM runs and etc. So in one server it is not possible, so LSF actually takes care of all the requests and fires say 100 here, 50 here, next 100 here, another 200 here, something like this. So your LSF is the one which takes your job requests, and then it plans and then executes the project, the jobs. Okay, and now the important commands, I have just captured it over here in the caps, but these are all kind of, you have to use it. All the Linux commands are pretty much, small letters. Okay. Thanks, Sonia, for pointing that out. Okay. So there are certain important commands. Now, you wanted to fire a run. Okay. Then it's called batch submission. It's called B, meaning it's a batch submission. Okay. Use the B sub command to fire the job. Okay. Now let's say you might have fired 5 different jobs. Now whether they are running or not, now you might want to check their status. It is called B jobs. Okay. And then you wanted to now say there is a run which is not going good. Now it is either it is kind of erroring out, or you realize that, oh man, there are some inputs that I gave wrong. Now you want to kill that run, so you wanted to use this command called b kill. And then you may have different queues. Say in a company, if you look at, you have a PD team, you have a DV team, you have a DFT team, and you have a RTL team. Okay, and then you will have a regression team. Okay, say now there may be a different queues for people. Okay, so PD team will have a say set of server dedicated for them that would be put in one queue, and the DV people, design verification people, will have a different number of servers allocated for them, so that will be different queue. So you might have, there is a command called b queues to see what are all the different queues that are available and how much is kind of, how many jobs are running, how many of them are pending. So it's a kind of your total LSF summary. Okay, now that is, bq is you used to get that information. Now b hosts. So b host is basically, say, in a particular queue, how many servers and what are all the server names and how they are loaded and everything, you can actually check it. So you can also use b host to get the server details. Okay, so LSF is the one which actually used to launch the jobs and which manages the load of the servers efficiently. Okay, and sometimes you might need more number of CPUs. So LSF divides the requests, say, kind of, as I said, so first 100 jobs that runs here, the next 50 things going to be here, and etc. So the term multi CPU is very common in industry. Okay, so you might wanted to run this with 8 CPUs or 16 CPUs and etc. Okay. Okay, just a quick glance of what is this tickle scripting. So, as you know, we are implementation persons, right? So we work pretty much with the tools. Okay, now we use the commands, tool-based commands. Now that is exactly what the TCL is, tool command language. So there is like any other language, kind of, you have a C, C++, and Perl, and then Python and all that. So we have a different, languages. So TCL is one of the language, and to be honest, it is pretty easy to learn. Okay, and remember all the EDA tools. Probably I can say all the tools in VLSI domain uses TCL for sure, and some tools uses these days Python. Say for example, Redoc uses Python, and that's the only tool that I'm aware of. But all the other tools pretty much uses the TCL and TCL environment. Okay, now the TCL scripts basically, you define what is the first step, what is the next step, so it gets executed one by one in an order. Okay, now if you look at here, see, even in my area, if you look at here, so we have got a lot of scripts. So if I have to show you, see, all these are all kind of, tickle scripts. Okay, all these are all kind of the tickle scripts. All right, so pretty much in each and every environment you will see the tools, and then the scripts, supporting the TCL. Okay, and probably you might, you might want to learn TCL scripting, and then you can actually automate a lot of stuff. Say for example, you might want to create a routing blockage over and around the macros, and then create a bunch of placement blockages in a given area to take care of your congestion. And then you have a timing violation, so you might want to generate the ECO automatically, say kind of HVT to LVT swap, or X0 to X1 upsizing. Okay, all that. And then you might want to do some analysis, so you might want to get the setup margin or slack for all the given endpoints, and then setup aware hold fix. So you might want to get create ECO, it's kind of looking at setup aware hold fix method, setup aware hold fix. And then we also use a lot of scripts to fix the DRC violations. Okay, so you may have a lot of spacing violations, and then you may have a lot of VR related issues and etc. So that may be in terms of thousands. Okay, and it may be across all the blocks. So you may have a 30-40 blocks. Okay, now say every block is having violations. So now how do you go about it? And then you know you cannot obviously sit and fix one by one. Now we come up with this TCL scripts which would go and fix and all of that. So you need to learn TCL scripting if you are working in, say, I can say like kind of RTL synthesis. Okay, and then DFT, and then if you are a PD engineer, and then you are an STA engineer, and then you are an IREM, and then you're say PV. and then you are kind of LEC person, and then low power checks person. So for all these engineers, TCL is going to be a basic thing. Okay, so what I suggest is, if you are working already in any of this domain, you should be improving next, or the next plan should be learning TCL scripting. And if you are looking to get into industry, um, have a basic idea of what is TCL scripting. Okay. Okay. The run. Okay. The PD flow. Okay. Why we say CAD flow? Okay. Say a simple thing, right? Let me just explain you an environment how that is actually being done. See, you have a CAD team which keep delivering your releases. Say latest updates. Okay, latest updates. So they keep saying, okay, version number 99, version number 100, say version number 101, say 102, say like this 103, and say 104. Okay, so the CAD team is general, centralized team where they keep coming up with certain releases. Okay, now these releases could be bug fixers, or these releases could be a design related bug, tool bug fixers or flow updates, enhancements, and etc. Now say for example you are actually working in project A. Okay, see, you might be asked to use version number 100. Okay, for your current runs version number 100. Now you find a bug. Okay, you find a bug, so you are using version number 100. Now you found a bug in the flow which is not doing the right thing. Okay, now when I say that, it is basically, you can say, you have to report it back to the CAD team, that bug. You know what, you are actually working on your design implementation. Now what these guys would do is, now they look at, now they fix that bug and they release it like kind of say 105. Now what you have to do is, now you have to pick your version 105 for your implementation next time, next runs. So this is how it actually happens. Say for example you have a project A, project B, say project C. See, each of them will have their own bug, requests, enhancements, and things like that. So, CAD team will take each and every request. So, they keep updating and they'll keep communicating that, hey, version number 105, these are all the enhancements that we have done. Say, version number 110, these are all the updates that we have done. So, you pick if you are looking for these updates. So, this is how we actually work in the industry. So, CAD team is going to be a centralized team which would keep working on the flow and they keep testing it. In the meantime, they also get a lot of requests from different PD teams. Okay, and then they keep delivering you the latest updates and etc. Okay, so this is what the PD CAD flow is. Okay, now the runs are continuous without any time delay. That is the main reason behind we having a Makeflow, and helps quicker turnaround time than manuals. And all the stages are run one by one in a defined order, so you don't need to kind of missing the order, or or say uh, running the different targets randomly. So it is all run in a defined order, and avoid manual errors like missing stages. So you might have missed it. So I had a scenario where one person have completely missed CTS, and they went and ran next things, but we found that later, and it is kind of created a lot of havocs. Okay, and then helps you a lot when you handle 3 to 5 blocks. See, remember this, in industry you will never given one block, you will never be given one block, you will always look at minimum two. And there are companies who are kind of having a solid flow, you will like be even given up to 5 blocks. So I know a couple of companies where they people work on 5 different blocks. Okay, and then all the updates are done in the central area. So it is like kind of all the updates, as I said, right? Like you may have a project A guys may request something, now that is done in central area, you pick whatever that you want. Now project B is kind of again requesting something. So that is what I said, the flexibility. The CAD team will come up with the flow in a such a way that is a much more flexible with respect to your designs, with respect to your technology, with respect to your tools, with respect to your designs. And that's like kind of what blocks or which project and etc. Okay, and then they will have the better integration, or the LSF integrated in the flow. So it helps in effective use of infrastructure, and then lot more. And remember, why do we need flow? So when I have a 30 people, 30 people working in a project. I may have, 5 leads. Okay, I may have, kind of 10 senior resources. Then I may have another 10, say junior, less than 3 years, and then I may have another 5 entry level. Now all would be given a blocks, and each of them would be working on it. Now the entry level guys may not, maybe just starting their career, or juniors also may be very, early phase of their career now. But I have to follow certain process and a certain steps. They have to use, say for example, simple tap cell distance of 50 micron, and they have to add spare cells every 80 by 80 or 100 by 100. So I cannot go and tell them individually. So that is the main reason we have a CAD flow, where you have to, so everyone follows the same steps, as simple as that. Okay, so that is the advantage of you having a CAD flow. Okay, so that sums up my, the presentation part. Now I will show you how I run my, the runs. I just need a minute to bring up my environment. Okay, how I'm actually going to run. See, now if you look at here, I have got my inputs over here. So it is like kind of, USB top net list. Okay, and then I have got my SDC, and then floor plan def that I have got. Okay, these are all my inputs. Okay, and then I have got my scripts. Okay, here where I have got my tech setup, which
Sir,
will have, sorry.
your screen is not visible, sir.
Okay, can someone confirm that you guys are able to see the screen?
Visible, sir.
Yes, we are
Visible,
able
sir.
Visible, sir.
Yeah, it's visible, sir.
Okay, if someone is not able to see the screen, please maybe you log out and log in. That would actually help, because everyone is able to see the screen. Okay, so now I have defined all my, the inputs, which are kind of, libraries and all the things, what cells that I'm going to use and everything, what corners and all that. And then I have got my user setup, where my design details. So tech setup is common for everyone, and user setup is, people can, say you are working on a block A, and the other person is working on block B, so they can actually customize everything in this. Okay, so now I'm just going to run, say, make import. Okay, that is my first step. Now when the run is going on, so now the run is actually getting started here. Okay, it invokes the tool automatically, and then now when the run is going on, what is it I need to check is, I need to check the log files. So these are all old log file. Let me just delete it. Okay, now if you look at here, so make import is done. Say what it says is, so basically import design stage is completed. Okay, now if you go on to check, okay, let me just remove the reports also, so that like I can show you guys. I'm just going to rerun, because there are a couple of directories that you be created, so which is, so I'm just rerunning make import. So I don't need to type that, okay, ICC2 and what inputs, and GUI based work is not at all going to work in industry. And we use GUI only for debugging purpose. Okay, so the design is kind of imported now. Okay, now if you wanted to know more details, say for example, you have the log, say for example, import log. Okay, you just have to check. Okay, so these are all the informations that you can actually go on to check it out. Okay, what corners that you are defining, and SDCs that are being read and all that. Okay. And and if you look at here, what directions of those metals and everything, what layers are allowed, so all these informations that are defined in your run script, and you see all that are being printed in the log files as well. Now what I'm going to do is I'm just going to run make route underscore opt. Okay. Now you can just watch it here. See here, it's kind of the floor plan. So I'm just using this. I've already done the floor plan, def, and I have written it out, so it would pick that automatically. So you can just watch out. Now it will actually performing. The floor plan stage is completed. Now you know what next. It is already starting the pre-play stage. Okay. See here, it is actually starting. So it's done with the floor plan stage. Now this all possible. It's just with the help of your make based flow. Okay. Now, what it says is here, see, it is a pre-play stages, kind of say it's completed. Now, what is the next thing? It is going to perform the placement. Okay. So now let this run all the time, let it happen in parallel. Now you see here, there are logs that are actually kind of getting created. So you need to refer these logs. Say, for example, now pre-place.log. Let me just open that. And then what I check here is, say, I just check for errors first. Okay, so this is not an error. Okay, now this is not an error. This is not an error. Okay, so there are no errors. And then say warnings. Okay, see here, it is a kind of say some warning that you need to look at. Okay, and then okay, so something is here. So this warning. Okay, you need to review all these errors and warnings. Okay, so you can open the log file and then check, and then what and all it is actually executed. So you are actually say sees here, right? You're seeing that okay, there are a couple of spare cells that are executed. So when you refer the log file, you will have all these informations. Okay. Now not only that, so you have got reports. Say for example, when you run the import, it automatically performs sanity checks. Say for example, your check netlist. See, you can actually go and look at your reports in the report directory, where you have your all the netlist related issues that are kind of reported. So you might want to review all this, and the same way your check timing as well, basically your time SDC sanity checks and everything. This is your summary. So this kind of the input port is not having a clock relative delay. So there are 1114. Now you know what you should do. You need to pick all the messages and get these ports. Check with your STA team for your SDC update, or if they are okay to waive. Okay. So now if you look at here, it is actually running something, but I don't know what it is running. But if you wanted to know, just go and do logs directory. It is running placement. Okay, it is running placement. So that is how it is actually going to execute. That is how we actually execute the projects in the industry. Okay. So it would take time because the designs are kind of usually takes little good amount of time. Okay. Now I can show you maybe one of my other things. Okay. Okay, so here your placement stage is completed. You see that? Now I'm not doing anything. I'm not running one by one. Now the next is automatically CTS is getting picked. Okay. Now what I need to do is this placement is run. Now the first thing is that I need to do is, so now logs place lot log. You need to go and check as usual. So warnings, errors. Okay. What are the errors? Okay. So it says no errors. Okay. And then warning. Okay, see here, no clock routing rules specified. So why is it looking for it? So you should actually look at, okay, is it really necessary at this point of time and all that? Now say hierarchy boundary restrictions detected. So you should actually check what is this warning is all about. You need to work with your cat team to understand, do you really need to fix this and things like that. Okay. So checking your log file first, and then you have got your reports. So now you have got your place reports. Now you look at here, what and all information. See here, I have got my timing report. Okay, so now this is going to be my timing. So it says no violations. Okay, but you can actually always check. Say for example, now QR report, it will have all this summary, timing summary for the corners that you are actually defining. So that is, we call it something like kind of multi-mode multi corners. Okay, and okay, and then, so as I said, right, like say I have got my utilization threshold voltage group reports. See, this is how the reports. Okay, now see, I have got these many cells and how much percentage. So I have not allowed LVTs, so it's, I have used only HVT and RVTs. Okay, so you can actually check this kind of report that would be usually dumped. Now see here, you have got other things. Say the map, congestion map, your design map. Okay, say for example, okay, so this is your congestion map. So there are no congestions here. And then you have got your, cell density map that you can actually open and take a look at it, in which areas you have, the, you know cell density is on the higher side and etc. So this is the advantage of you having a flow where you keep running in parallel. Okay, and then the other things, you can check your log files and everything, when the run is in progress. Okay, so CTS is already done, and then right now it is running post CTS. Okay, which is basically optimizing your timing, both setup hold, and the DRV setup and hold, because we have done the clock tree building. Okay,
So, like, if we want to branch one CTS run in using Makeflow, how do we do that?
you can
Like
actually
one
do
run
that.
only?
Okay, so what you can do is basically you can actually copy this whole directory. Say for example, now you have this. Say ideally I supposed to do it like kind of run one, run two, run three, like that. But now say for example, if I wanted to do this, say for example, what I can do is say CP minus RF, say this USB top. I can just say this whole directory, I can just copy it. Say this is run two. Okay, now I can go inside and let me just show you that. Let me. Okay. Okay, now say I go inside this. Now I have ran all the way till CTS. So you want to read and post CTS. So you just need to say remove this post CTS, and then if you run it from here, it's like kind of say make route opt. Okay, it will actually run from post CTS only. So it will reuse the other data the from the directory where you just copied the data, no? So it will reuse the data. So that is how you can actually branch runs.
If we keep on copy for parallel runs, then it would be a wastage of memory, right? So instead of
No, no,
doing
no, no, no.
that,
Okay, see, Sonia, see, there are a lot of ways that you can actually do it. So that's all different. Corporate level, they do it. You can actually link it. Otherwise, if you really wanted it, you instead of copying, there is something called soft link. Okay,
yeah,
so you
yeah.
can do that also. But see, that's what I'm saying. So it is like kind of, there are many ways. So it's just, if you are, see, industry uses, create, say kind of, I work for AMD, they have something called tile builder, and they create a branch, tile builder branch, create init branch or something, and then work for Broadcom where they have Makeflow, and you just execute it the way you want it. Either you copy it or you link it, it's up to you. Okay.
Either the way like we change the destination of the uh, target, that would also work fine, right?
uh, See,
Like
I can
even
see,
public.
Sonia, see, I maybe you can actually, can I answer your questions towards the end?
Yeah, yeah. Okay.
Because it's too deep, see, there are many people who are not even in industry, and I'll explain you, definitely, please don't go away. I'll explain you everything. Okay. Okay, now if you guys look at here, I have completed the route of stages. Okay, you see here all the stages, and then all the way till route I have completed. Okay, now what is the next stage? So we are done with routing. Then the next is going to be a extraction. Okay, Now what I'm going to do is just say make extract, which would actually perform your star, the spiff, which will automatically invoke the tool called star rc. Okay, so let this run keep going. Now we will actually look at the logs. Okay, so you have got a route of log. Okay, so your log file will have the information. Say for example, now if you just check for at, it will have the violations details. See here, it says there are violations. Okay, so it goes into iteration. So basically you need to check, okay, how many drcs and then how many things are there and all that. See here, the first iteration had kind of say 105 violations. Okay, fine. So there are different categories with different spacing. And
890.
guys, can you please go on mute? Okay, now so you might check what are the different types of categories of violation, and then the next iteration. Okay, from 105 it came down to 12. So that is how the tool actually goes in. So it in the end, what is that it is there. Okay, it is almost like left with only two shots or something. So it's not bad quality, it's a good quality if you ask me. Now it is actually running the extraction. Okay, now if you look at here, so I have a directory called outputs where we write out the details from your route db, each and everything. Say you need a .b for your pt runs and pg.b for your conformal low power runs, and lvs.v for your physical verification runs, lvs purpose, and def is needed for your irem purpose, and then you need it for your dmsa purpose, and gds it's basically oasis. Okay, and then your left, which you need to share it with your top level, and this is the spiff that I would actually would be using for my pt run for sta purpose. Okay, and see, it is like kind of, it is, I've already written out a spiff which is kind of say c worst and 125c, and you may have different spiffs. There is one more spiff which is kind of being run here, c best. Okay, so once that comes out, the next thing that I would be doing is I would be running the prime time sta. Okay, see here, now I have actually, kind of two spiffs that are dumped automatically just because of my make flow that is kind of, having, we have defined it, right? So it is kind of what is the output requirement. So I have defined only two. It's just for learning purpose. So it is kind of, but in industry, you may have a 5, 10, different number of, spiffs for different, sign off criteria. So now I just wanted to run STA. Now you will see here, these are all the corners that actually automatically I have defined it, which would actually run my invoke pt and then reads all the inputs, and then performs and writes out the data. Okay, and it runs for each and every corners, which you don't need to sit and run one by one. That is the goal of your make flow. Okay, now if you ask me, it is actually running three different runs and then it is done. Now if you go and check, there is a folder that is kind of created sta. Now inside this you see this different folder, so funk mode, and then ss.95 125c corner and things like that. So you can actually go inside that and then check. Okay, so you have got logs. So log file is the first thing that you need to check. Okay, what and all is being read, errors, warnings, and everything. So basically you need to check the whole log file. And then you have got the reports. Okay, so various reports. Okay, you have got your the spiff annotated parasitics report. Okay, and then qr report, and then your setup, hold, and drvs and everything. And then you also have your db saved. in case if you want to invoke, load the DB and debug something in the prime time, your DB is also kind of saved here. So that is the advantage of you having Wakeflow. So if you ask me here, so this is a corner. See, let me see if there are any violations and things. Okay, you see here I have got my setup violation. So now I need to go and fix them. Okay, now how will I go and fix this? So now what we will do is we will try to use the DMSA based thing and then generate the ECOs and etc. Okay, so we have got a set of violations, but before that, let's check if we have got a hold violations. Okay, okay, so I think I'm good at setup hold violation. There are no hold violation, but only setup violation. So let me just run the timing ECO generation. Okay, now I'm just going to perform the DMSA based physical aware ECO generation. So it is kind of having three corners and it is kind of launched three different jobs which would go in each of our things. And it is going to now create the come up with the ECOs. Okay. And again, when you are running something like this, the runs will keep, printing a lot of messages, which would you will not be able to see everything because it will keep printing and pausing the screen and it will be keep on running. So you should always look at your the log file. Okay. Okay, now you see here, it's just performing the timing fixes, iteration one. Okay, it is kind of, seeing total how many violations in this corner 72 and in this corner 75, in this corner 39. So total 186. So it is kind of creating the plan for fixes. It is kind of saying fixing the violations. Okay. See, just wanted to emphasize only one thing here is that, see, when you are an experienced person, okay, you should be able to come up with your own flows. So, like, that is how you add value to the company and you add value to the projects, and then you increase your, knowledge and you become a critical resource. Okay. So you should improve your skills on PD concepts and then if you ask me, STA, sign off STA and PV, and good thing, if you are good in scripting, then look at how to automate your DRC fixers and everything. So that would actually help a lot. Okay, so it kind of gets into multiple iterations and then fixes. Okay, and these are all your DRCs. When I say DRVs, max cap, max tran and all those things. See, it says that 942 max cap violations and all that. And there may be some things that may not be able to fix. It would actually leave it, okay, saying there are certain reasons that it's not able to fix it and etc. Okay, so let it run. So you hope you have seen the Makeflow, how it is actually helping in terms of automating, and you don't need to sit in front of PC. Actually, you can just fire it and you can just go for your break, or some people might go for lunch, fire the runs and go for a lunch break or tea break or whatever it is. So it actually helps a lot. Okay. Now it actually come up with, it's kind of, written out the ECO here. You can say writing changes, it is into this file. Now, if you look at this particular file, okay, you see here, now my ECO is ready, which is kind of with the locations. This is what we call it, like kind of, the physical aware ECO, which would actually help your design closing much faster. Okay, so this file now you can actually roll in the route DB using the route DB. Okay, you can just say exit, you're done. So we have generated the ECOs. Okay, all right. So now I think this lab thing, that's all. I want to stop it here because I want to have a couple of, there are a lot of question and answers, questions I see. I wanted to dedicate some time for question and answers. And you can actually learn everything. In case if you're looking to learn, you can get in touch with me. And so this is our, contact details. You can just note it down. Okay. So I'm getting into the questions and answers thing now. I'm just going.
Hello.
Yeah, go ahead.
So before you
So,
close the tool,
One at a time,
uh,
please.
hello. Sir,
Yeah,
am I
go.
audible?
Yes, you are audible.
Before you close the tool, could you please show your technology file?
Okay. So this is my tech file. This is how it is going to be. It's like kind of, a lot of things. All these
Okay.
informations, like kind of, when it comes to a metal, see, this is a metal 2. Now if you look at metal 1, so you wanted to know more things on metal 1, see, this is the section of where your all the rules, what is the min weight, min spacing and everything, and what is the fat table spacing, and then your dummy metals and vias. This is a tech file.
Okay.
Okay,
Sir,
there was
why
a.
we need multi modes apart from corners?
Okay, there are, see, when you look at your design, right, so say simple, right, like you are using your mobile, it is actually a functional mode, that functionality which the chip is designed for. Okay, now, so before we give it to a customer, say for example, now say I am company ABC, and I, say OnePlus is coming to me and asking me a chip for the next generation mobile. Now I have to design a chip and then test it, ensure that it is kind of, we have, what do you call, uh, we have to ensure that the chip is actually working, right? You cannot deliver a dead chip to or non-working chip to a customer. It would be a, that's your end of business. Okay, so now to test it, you need to have your different methods. So one is you need a scan shifting, so there is a stuck at false, and then there is a transitional false, and then there are different ways of identifying the faults. And you may have a lakhs and lakhs of paths. Okay, say simple, now you may have a design like this. Okay, now there may be a paths like this in terms of lakhs and lakhs. Now say there may be a failure over here. Okay, now how do you identify, okay, this is the path that is actually failing? So you have a scan shift, that is for scan chain, and then scan capture. Okay, and then scan at speed. Okay, now if you look at, these two are executed with the frequency of 100 megahertz. Okay, now this is actually executed as same as your functional frequency. Okay, so that is the main reason why we use different modes. Okay,
And also same thing, sir. Like one more question. Like there in some designs I have observed, like they have generated the clock, okay, from one master clock, but it seems like the same period of the master source clock only. So why that is needed if it is the same
that is meant for
period?
crosstalk, better crosstalk purpose, crosstalk analysis purpose.
Yeah. So if you have any like, if you don't mind, a little elaborate.
Maybe I have other questions actually. You can get in touch with me. I can help you out. Ping me in WhatsApp. I can help you out. Okay,
Yeah. Yeah.
because that is
Okay.
a too
Sure.
technical. Because I have a lot of other questions which I wanted to cover. Okay.
Okay.
Anyone
Okay. No
else you have
problem.
questions? You can
Definitely.
unmute and ask, and then I will actually walk through the questions that are in chat box.
hello. Yeah, hi.
Hi,
This is Praveen here.
hi, Praveen.
So, I observed that there are pins off track in my place macros. So, but I did not fix. I went up to the place. So, can I do it in the place by snapping it? And if yes,
What technology that you are working for, Praveen?
6 nanometer.
I don't think you can actually move the macro incrementally at play stage.
No, I'm just talking about selecting those macros and snapping it. And if I do that, will it affect the bound buffers?
Is that going to make your macro move?
No, bound buffers, not macros.
You
Ports,
said macro.
ports.
You said macros.
Oh, sorry. Ports, ports, ports. So ports are pins off track.
You need. Okay, let me give you. So the process is, now who gave you these pins? You placed it,
Sir
or is
came.
some? No, no. Wait. Let me.
I
Let me.
placed it. I
So
placed it.
you placed it. Okay, fine. Now there are process. See, if you get the pin placement from the top level, then you need to work with your top level and ask for a better pin placement. Okay, that is a one method. Now, if you have created it, then you can actually move. Make sure you snap the pins on track when there are certain settings that you need to enable before you place the pins, or at the time of placing the pins you need to enable snap to track or something like that, and then place it. Now in case by mistake you have missed it, now there is, you should have caught it with the check pin placement command. There is a command called the check pin placement. Now that you should have ran it and caught it. Now you missed that also. Now you are in the play stage. If you are just only snapping little here and there, you can actually do that. That's not an issue at all, if you ask me.
Okay, in play stage itself.
Yeah.
Okay. If I directly give the command without giving the names of the
No, you
ports which
no.
I have placed,
No, it is. You
so
should
will it?
always no. The way I suggest is you should get the pins that are, or the ports that are not in track. You should get that by running check pin placement or verify something. There are certain commands depending on the tool, and then you take that and you try. Only use, move them. I don't want you to globally
Mhm.
move them. That might, because you are
Okay.
in the placement stage. Okay.
Okay. One more question. So I'm observing some timing violations due to path margin. So can you
Uh,
just explain me some more something
Praveen,
about path
Praveen,
margin
Praveen,
and
Praveen, this is actually advanced level. You can actually get in touch with me, because there are many people who are kind of entry level. You are talking in terms of design implementation, advanced level. You can get in touch with me. I'll surely definitely try to help you out. Okay.
sure, sure, sir.
Okay.
Yes.
Any other questions?
Thank you so much.
Yeah.
Yes, sir, I am Nagaraj Sharma. Hello.
Yeah. Hi. Go ahead.
So actually, you have told that we how to make file. So, but we don't know how to write the make file. Is there any source to know?
So you can actually use Google only. See, I kind of learned, see, to be honest, even there is a page where I can say it's kind of I have even referred these kind of pages. Say, it's like there are a lot of materials in that actually. So you can actually say this may not be with respect to VLSI. That is a big thing. Okay, so you should know the syntax and then connect it with respect to the VLSI target. Say here it says just say hello, but if you look at in my Makeflow, I have kept it like kind of say plays and etc. So something you can use the Google pretty much to learn the things.
Okay, sir.
Okay, I think I wanted to spend some time on the questions that are on the chat box. Okay. Uh, okay, I'm just coming from the top. Okay, so macro placement guidelines. So that is all, because each macro comes up with certain guidelines. So you have to there are poly requirements, OD requirements. So you have to change. You have to honor that. So that is the main thing. Okay. Okay, so you're talking about physical design course. So so there are people who are kind of asking for the courses. So we have, kind of physical design course, which is kind of, I don't call it a course, it is a kind of mentorship that I call it, where we handhold the people, and it is a kind of, we have a hardly 15 member per batch, 15 to 20 max, and there's a syllabus where we have a kind of, complete basics, okay, and then implementation, and then complete sign off checks. So everything that you have a hands on, except the IREM, and then one thing, we have got PT tool, and we have got ICV and everything, and then advanced topics. So that's the beauty of our our mentorship. So you get to learn about load power methodologies, and then you try to learn the UPF, and then tickle scripting. You get a chance to learn the basics of tickle scripting and advanced STA concepts, like kind of timing closure with respect to that, and then now whatever the DMSA that we have ran, physical aware ECO, now in depth of it, like kind of say you have a path. Now how do you go about looking at the path placement? Now you wanted to look at what kind of violation it is, what kind of cells is that in a congested area. Now to that level, looking at your DB, and then coming up with the fixes, and then you also get to learn, chance to learn setup aware hold fix and everything. That is advanced STA. So OCV, POCV, PBA, GBA, and then latest things, LVF, and all that you get a chance to learn. And then you have many people are kind of almost 95% of the companies are working in FinFET and double patterning. So you may have a lot of theory that is available in the internet, but let's say, what is that, as a PD engineer you will see a challenges. You get a chance to see, learn in terms of implementation, what challenges, what is the meaning of double patterning, what are the DRCs that you need to take care, and how this affects your macro placement and standard cell placement. What is the meaning of pin coloring, routing coloring? Okay, what is the meaning of mask, track offset, and all that? And then we also give you guys the 7 nanometers, 16 nanometer, challenges, floor plan guidelines and everything, and you again get a chance to learn Makeflow and LSF basics. And we do have got multiple designs, so where you just have to, you find your own time and run it. We have got almost like a close to 10 different designs, so which you can actually make use of it at the time of learning. So that is your course, and the course duration is going to be say kind of 5 months. So it's 20 weeks program, covers all the way things. So it is in depth. So what we say is like kind of we guarantee the knowledge which is close to 3 to 5 years range. I can guarantee you a knowledge of 3 to 5 years at the end of the batch. That's the basic thing. Okay, that's on the course. Okay, so there is a next question is basically full chip integration. Timing will be violating or not. So interface timings would be violating. So full chip meaning it is the kind of, you will have a into rich paths, rich to out paths. They might be violating. You will get a ECOs from the top level STA team. Okay, which domain is better to start our career, DV or DFT PD, depending on the salary. See, what is your interest? So is it like kind of, are you good in programming? If you are good in programming, you like programming, DV and DFT could be one of the chance. But pretty much, many people, who don't, many people, didn't want to do get into programming side, but they all choose PD. So PD is kind of, 5 to 10% scripting skills needed, but it just, you don't need to even, have a programming skills, but you have to modify the existing scripts. So if you ask me, like, I have a scripts which I gave you, say simple, I assume that I am giving you this pre-placed article. Now you might have to know, okay, what is this step is doing. So that much amount of knowledge is needed. So if you're good in programming, you can choose anything, but PD is something that you don't need programming. But remember, all the technology related challenges that are, seen by only PD guys, and PD salary is top notch than any other domain, if you ask me. There may be people who might be, arguing with me, or you can come for debate, but the market wise average salary is, as per my understanding, it's like kind of, much better for PD. That is why I'm in PD. Okay. Next, is there any thumb rule for floor plan routing utilization? So it is starting utilization should be, standard cell utilization should be around 60. So anything beyond that, starting higher, you might have a trouble, and you starting lower, too low, it might be a penalty for area. And it is, if you are working in a CPU based designs, then it is totally a different ball game altogether, because CPUs would be, always targeting a, 80% or 85% end utilization. So it all depends. Okay, the next question is, how do we check report missing, all that?
Sir, same question like, is there any
డబ్బుల
thumb
టాపిక్
rule
ఏదో
for
చెప్పావు కదా.
congestion analysis in
ఎంత
lower
ఎంత
technologies?
సంపాదించావు?
It
Like
is
this much percentage or like that? Like both horizontal and vertical should be this much percentage like that in lower technologies, any thumb rule?
okay. So it is like kind of zero point 0.5 to 1 is what we say. But again, you need to look at your cell density, pin density, which area, how they are distributed and everything.
Okay. Like in higher technologies, I saw like it is a thumb rule like should be 1%, not more than 1%, like
It is, there
horizontal
is no
should be
change in the
0.5.
thumb rule. There is no change in the thumb rule for any technology. That is nothing to do with the technology, if you ask me.
Okay. Like the congestion will be more in lower technologies, right? So just wanted to know if there will be
How
any
do you say that congestion will be
change
more
in
in
thumb
lower?
rule.
No, let me ask you this way. How do you say that congestion is more in lower technology? Is that congestion is related to your technology?
No, not like that. As we are using more number of metal layers and more number of cells
No,
will be used in lower
no,
technologies per meter, right?
no. So maybe there is a clarity missing actually, but congestion is purely depends on your design and the types of cells that you use, whether it's a 6 track, 7.5 track, 8 track, 10 track, and what is the area that is occupied by PG routing, and how, so there are many things that you need to look at it. So
Yeah.
I'm still, I'm sticking to the same answer. It's like kind of zero point 0.5 for before, before CTS, and 1 before routing.
Okay, okay, yeah, sure. Thank you.
Okay, so the next question is Amit is asking like, how do we know what frequency we have to start? Amit, there is it's see, it's not that you are starting a project and you are identifying a frequency. It is always you get a project with the frequency as a target. So that is a spec. So not like you implement and then you increase the frequency. That is not the case. Okay, Sri Lakshmi is asking like base DRC, we'll come to know all n-well spacing, all this after placement only, right? No. See, you will actually do a floor plan DRC. So in the lower nodes, floor plan DRC checks are basically, you do a complete floor plan, then run placement with low effort, or different company follows different flows. Okay, then run FPDRC where you run only base layers and you can ensure. So in the lower nodes, there is something called floor plan DRC which you need to run. Okay, and that is on that. And then how many of you are 2018 or before passed outs? Okay, okay. Why is the need that Brahma 2018 or before passed out? Brahma, may I know why are you asking this information? If the congestion is there in the design, how timing would be. So because of congestion, your tool might detour them when it reaches routing stage. You'll have congestion in this area, so this detour will affect your routing. It might add a lot of cells, buffers and inverter pairs for your tran fix. Then it will actually kind of increase your delay. You will have a timing violations. Certificate. No, I don't think we are actually offering certificate for this. But if you join the mentorship program, yes, definitely. Okay, and okay, RTL version or tool version. Slide number 12. What was that that was mentioned? There is nothing versions. I'm not sure. If you are online, just unmute and talk, Ramachandra. How
Yeah.
automation using make and scripting? Just give me a minute. So automation using make and scripting. So I think I have showed you the whole thing, no, Shubham? Just some time back. I know I have even showed my whole infrastructure and everything. Are you there, Ramachandra?
Yeah, yes, Kumar.
Yeah, go ahead.
While
So
you are explaining, you use the terms like 99, 101, 104 versions.
okay. Those are all flow scripts. It's not RTL. It is like kind of CAD versions. So it's just a revision control.
Okay.
Yeah, it is just a revision control because they have to track the changes, no? Correct. Yes, CAD team also will be multiple people and they cannot keep giving it, that's the way we manage the whole projects, the area. Sri
Yeah, like
Lakshmi, yeah, sorry,
it's
go ahead.
like updating in the scripts.
Yeah, right.
Okay, thank you.
But you need to keep the revision of each update. What if you want
Okay.
to tomorrow revert back to old update? Okay.
Yeah.
Yeah.
Okay. Got it.
Okay. I think Sri Lakshmi, I just explained, I believe. Can we get the recording? Yeah, this recording I will share it with all of you, and then I will also upload it in the YouTube. So you have got a lot of YouTube videos actually. Our channel. It's VLSI Mentors. So you can actually go and have a check over there. So you have a lot of videos, which is kind of we just keep giving sessions often. So you can actually go and watch those. So there is a EDA scripting and automation, and then CMOS, and then so you will keep hearing a lot of sessions that are being coming in the upcoming days. Okay. And what is the other things? Questions? Is there any way to access previous logs of that stage? See, if you wanted to preserve logs, you should get in touch. Basically, I have a mechanism to move them each and every log file. Okay. There are modes like functional mode. Okay. I think, sorry, if you do process running ticket.
Sir,
Yeah, go ahead.
when we do a make clean and the previous logs will be override, right? If you again restart the run, then how to access the previous
No,
logs?
so that is what. So you need to
Yeah.
give this request to a management of your CAD team where they have to find a method to backup it. They
Okay, sir.
should
Okay.
move it, when they are starting the first stage, right? They should
Yes.
move the log folder to a backup and then they should create a new folder. That is the way I
O-
should do it. I would do it.
Okay. Okay,
Okay.
sir.
Yeah. Okay. So the course fee is 60,000 plus GST, and it is, you will get a tool access. We have a hall access, multiple designs, and the whole synopsis tools, and unlimited usage. There is no restriction on tool timings and things like that. You can have it everything, and we do have both online and offline classes. Okay. Advanced PD already for trained people. Sri Lakshmi, I think you can get in touch with me. I wanted to understand. So I'm actually planning for advanced clock tree synthesis and advanced partition and implementation. So you, so that you can become a full chip person. I'm actually
Yeah.
working on that. Okay. Yeah.
Okay,
Uh,
sure.
yeah. So, and even advanced STA. So it's basically, I'm expert of all that. So I'm just trying to, setting up the whole, materials and then things. Then we'll launch it soon. You can get in touch with me. Okay. Yeah.
Sure,
And
sir.
okay, between manufacturing grid, FinFET grids. See, grids meaning it is like kind of, manufacturing grid is the least minimum thing that you can actually move any geometry. Placement grid is something that, your cell's supposed to sit so that like you don't violate any placement legality things. And fin grid is something there is a, foundry requirement that you need to meet. So if you place the cells and macros in a placement grid, you will meet the fin grids as well. So how to fix an error in DRC? So you are talking about the DRC fixes. I think that we'll have another session on PV uh, in the upcoming weeks. I'll have that. Uncertainty hold. Why should we give hold uncertainty in synthesis stage? We don't do hold uncertainty, I think, but it is just a completeness of your SDC. The tool, even if you define it hold, won't look at it. The tool won't look at it, but it's just the completeness of the SDC. That's the basic thing. So Kumar, how mentorship? See, mentorship is something that I say, training is something that, it's a different term. Mentorship is something that I would sit with you for one-on-ones and then ask you, okay, walk me through what you have done, explain why you choose this particular floor plan, or why are you placing this macros. So training is something that may not be, so it is a kind of mentoring is something that I am sitting with you and hand holding. If you have, doubts that you are not able to execute, or you're stuck, I will sit with you and I'll show you how to debug and things. So mentorship is something that you're choosing a mentor for your life.
Sir,
Yes.
what is the completeness of SDC by giving hold value? Can I
So
explain
that
it briefly?
SDC would be you writing out and giving it to PD engineers. Correct? Now, so you have a setup uncertainty and you have hold uncertainty, everything, including the same thing. So set max transition and then set min transition, and then you have a set input delay, set output delay. So hyphen max, hyphen min. So there is something called, you have to have a SDC which is completely, say, I would say completeness, which means it covers both max checks and covers both, min checks also. That means setup checks and hold checks and everything. So but the tool won't look at those numbers before CTS when it comes to hold.
Sir, but we don't look CTS before CTS. Sir. After CTS, we looking at hold value. That's why I'm
Did
asking.
you understand what I said? I repeated this 3 times. Let me repeat one more time for you. You look at
Okay,
hold only after CTS. I agree. Your understanding is correct. Okay.
okay, sir.
Now, but even if you have SDC or your constraints with the hold uncertainty, the tool will not look at it.
Okay,
Are
okay,
you
sir.
going to read SDC after CTS again? So
No, sir.
at what stage you read SDC?
PNR statement, sir.
Okay. So you read the SDC at input stage, and you will not read it again unless otherwise there is a SDC update. Okay. So
Oh, sir.
your SDC should be complete in terms of your setup constraints and hold constraints and everything. That is the reason we define it. But the
Okay,
tool
okay.
will not look at those things. Okay.
Thank you, sir. Thank you, sir.
Yeah. Okay. So the fee for mentorship program is 60,000 plus GST. And common path pessimism. So that is something related to OCV and etc. Ramanayak. Uh, I would be coming up with STA session maybe next week or next to next week. I'll explain you at that time. Please do attend that session. That because I need to explain what is PVT variation, what is PVT corners and everything. Okay. Okay. So Sonia, you're asking. Okay, MSCTS. So no, that's what I said. Right? I'm actually kind of working on MSCTS, and then even Fishbone, trying to come up with certain different things. I would definitely, try to come up with for sure. Hold the time with respect to two flops. Sujay, I would be having a whole, the whole STA part in the upcoming week, so you can actually attend. That time I would explain. Okay, Kiran, you can get in touch with me. I can help you out. You are 2018 passed out. Okay, what is the cost of advanced PD and trained members? Uh, Karnay Hari Krishna. See, I have not launched it yet. I'm working on the content in terms of partition, pin placements, and bump placements, and IO pads. So I'm working on the design implementation for that particular thing. When I launch, I would be able to tell. Get in touch with me, please.
Okay, sir.
Okay.
Thank you.
Yeah. So, but one thing is that I'm not sure what is your background. You can just ping me. Maybe I can have a word with you and see if I can. You can actually get benefits from the current thing itself, current topics. Okay.
Okay, sir.
Okay. Okay, the next question is timing library in detail. Bhavani, I would need lot more time. I will have a different session for that. Okay, can we do a manual short fixing? Is it correct? So you would actually do that. So manual fixes of CTS and DRCs, the LVS and DRC issues is common in industry, and we do that. But in lower nodes, it is not easy. But in higher nodes and all, we used to fix it. So I have fixed almost like 1,000 plus shots and all manually. You know that and all. We do manual fixes. Okay, white tape cells are placed in checkerboard style to take care of your latch up. Okay, otherwise you will have a latch up issues. Okay. Okay,
So
I think,
tell
yeah,
about corner cells.
I did not get you. What was it?
Corner cells.
Corner cells, you're talking about corner pad or corner cells? What do you mean by
Corner
corners?
cells, sir. Like in full chip, we will be having
Okay,
corner cells.
say for example, you have like this. Okay, this is, say, assume this is your full chip. Now you have a IO pads, things like this, say like kind of this. Say you have a fillers would be, cells like this. So you will have a corner pads. You will have it like this corner pads will be used for your PG continuity. It's kind of 45-degree routing. You will have it. Okay, for that purpose we use corner pads. Okay.
Okay, sir. Thank you.
Yeah. Okay. Okay, Bhavani, you are asking a question on end cap cells. Why do you need around the macro? So why you need first of all end cap cells? Then if you know the answer for that, you would be able to answer for this question also. Okay, so it is to protect your inside cells, because at the time of manufacturing there is a n-well proximity effect. That is one. And the second is, if you try to place a logic cells at the bound at the edge, there are chances that they get damaged and your performance would actually change. So that's the main reason we actually have the end cap cells placed. No, end cap cells not placed around the macro. So all the standard cells are placed within the end cap circle. That's the right way of putting it. Okay, at placement stage we have congestion, but there is no cell density floor plan. Good. How can we fix it? Come on, you have a congestion, but there is no cell density, there is no pin density. Okay, it may be due to your routing. You need to look at your module placement analysis, Venkateshwarlu. You might have a lot of nets that is passing through, or you may have a blockages that are, put in that area, and etc. Okay.
Hi, sir.
Yeah. Hi.
Sir, for synthesis, we are having the input STC file. Output also will get STC file.
You need to write.
What is the difference between the both STC files, sir?
Just that you are writing out with expanded all the ports and everything. When you are writing a input SDC will have a get ports or get input star, but when you write out, it would be for each input, and all the values and all the syntax, everything would be properly defined when you're writing it out. Okay.
Thank you, sir.
Yeah, Sri Lakshmi, I think you can actually get in touch with me. I would actually help you, because it's been almost 2.5 hours. You can actually get in touch with me. This is my number. I can try to help you out. No worries at all.
Okay, sir, sure.
Because
Thank you,
it's
sir.
I've been talking continuously for 2.5 hours, and then people might get bored, or probably they would be like, "What is this?"
Yes, sir, yes, sir.
And okay, I think Ramachandra, you are asked. So there are some guys who are kind of raising hands. Can you guys ask questions? Okay, no, I'm not saying PD is boring. I'm just saying, it's a 2 hours sitting, in front of a session, or attending a session is not that easy. you know, it's for anyone, not, see, we are actually planning to come up with the interview question and answer sessions as well. So it's like kind of this. So just subscribe the LinkedIn, and then we do have Telegram group. Join there, and we would be having every week sessions from now onwards. So it's kind of Sunday. Probably we will try to have sessions every week. There will be one or other topic for next 6 months. That is how the plan is. Unless otherwise there is anything that comes up, but we will have a session on each and every small topic. We'll try to spend good amount of time and then go through each and everything. Yeah, you would get this recording actually, as I said, like I will be posting it. Okay, all right guys, thanks for joining, and it's good to see that a lot of people staying all the way till end. Hope you
Thank
enjoyed the
you.
session, and see you guys soon in the next session. Take care, bye.
Sir, one small request.
Go
So
ahead.
if you have time, right? So can you schedule a meeting like for only VCLP, this low power checks,
No, that's
only
what we
VCLP and
see. That see, I can actually do that, but I need to, I have other topics which are planned. Many people are asking different sessions. Okay,
oh, okay. Yes,
so VCLP is, that's what I said. Low power also is in plan. We would be actually working on, and you would be hearing from us soon.
yeah, sure, sir. Thank you.
Okay, yeah. Thank you, everyone.
Thank you, sir.
Thank you, sir. Thank you, sir.